Oftentimes people think about black holes as these gargantuan structures that form from collapsed stars. There's a big one in the center of our Milky Way galaxy, weighs 4 million times that of the sun. The photograph of a black hole in the galaxy M87 that got the world excited a couple of years back, 55 million light years away, billions of times the mass of the sun. But the reality is, anything, if you compress it enough, becomes a black hole. If you take an orange and you squash an orange down sufficiently small, according to Einstein, it becomes a black hole. The flip side of it is, we also typically have an intuition that black holes are really dense, right? That's usually the way we think about them. But if you make something sufficiently large, regardless of how low its density is, it will also become a black hole. So you can make a black hole out of air. If you have enough air, sufficiently large sphere of air, it would become a black hole too, with the density of air. So all the intuitions that we typically have about black holes, that they have to be dense and they have to be gargantuan, not right. And when you look at Einstein's equations, right in his mathematics, there's a little formula that you can see where it says if you have any mass m, whatever mass you want, and you squeeze it into a radius r that's less than 2 times Newton's constant 2g times m divided by c squared, speed of light squared. A formula, details don't matter. But you take any mass, if the radius within which that mass sits is less than 2gm over c squared, it is a black hole. Period, end of story, according to Einstein. But he never really believed that quantum mechanics was the true description of the world. And when he was developing the general theory of relativity, he was just thinking about gravity and not quantum mechanics. Stephen Hawking came along in 1974 and started to inject quantum mechanics into our understanding of things like black holes. And that's where Hawking proved that black holes are not completely black. He showed that black holes allow a certain amount of radiation to leak out of their surface, leak out of the event horizon, or leak out from just beyond the edge of the event horizon. And so, yes, when you think about black holes, as far as we can tell, they are a fundamental quality of the world, but you have to include quantum physics to truly understand them, and that's the cutting edge of what's happening right now. There's now a connection between quantum computing and black holes. But work over the last 20 years has established that when you have a black hole, actually even more general systems, but talk about a black hole, there's an alternate description of a black hole in terms of what's known as the holographic description. It's as if there's a two-dimensional world that surrounds any given three-dimensional world that has exactly the same physics as the three-dimensional world that we're familiar with, and yet it describes it in a completely different language. So a black hole gravity is obviously essential. That's how a black hole forms. But in this dictionary that physicists have developed, there's a description of a black hole that doesn't involve gravity, only involves quantum mechanics. And the beautiful thing is the quantum processes in that quantum world mimic the kinds of processes that people have been developing for quantum computing, quantum error correction code. And there's a dictionary that people have proposed for that quantum language on the holographic boundary with physics in the interior. And the dictionary shows that the quantum error correcting code may be the reason why space-time itself holds together. So there's this bizarre way in which everything that we know about in the world around us has a translated dictionary version in a different world that lacks gravity but has quantum mechanics. And so people are using some of the insights from quantum computing to understand questions about black holes and space-time. A wormhole is a tunnel, if you will, from one location in space to another location in space. And it's much like when you want to go from one side of a mountain to the other side of the mountain. You can go all the way up and over, or you can tunnel through, and that will be a shortcut. A wormhole would be a tunnel not through Earth, but through the fabric of space itself. And the remarkable thing is that if you have such a wormhole, and we don't know that they exist, but if you had such a wormhole and you're able to manipulate the opening, say take one opening near the edge of a black hole, where the rate at which time elapses at that opening will be slowed, then you can transform this wormhole from being a tunnel from one place in the universe to another to be a shortcut from one moment in time to another moment in time. The wormhole can, in principle, become a time machine. Now, let me just say, again, hypothetical ideas. They come out of the equations. We've never seen a wormhole. If we did have one, we don't know if we'd be able to go through it, but at least the math gives us this as a real possibility. If you take the two black holes, imagine, black hole here, black hole here. Each of them has a dual description in terms of a quantum mechanical theory on the boundary. If you then entangle those quantum mechanical theories, connect them with those yellow lines of quantum entanglement, it turns out that that's precisely equivalent to connecting the two black holes by, you guessed it, a wormhole. Imagine how we got two black holes, each described by this thermal quantum mechanical theory on the boundary. If we entangle those two quantum mechanical theories, there are these yellow lines of quantum entanglement, that's equivalent to joining the two black holes by an Einstein-Rosen bridge, a wormhole. If you are the object falling into the black hole, then you will, at least in the traditional way of thinking about black holes, you will fall in. You will make it to the event horizon, and in short order, depending on the mass of the black hole, the size of the black hole, you will find yourself increasingly uncomfortable as you get ever closer to the central singularity. You will fall in. If, however, someone is watching you at a safe distance, heading toward the black hole, their perspective on what happens will be different. And this has largely to do with this weird property of black holes. Time slows down near the edge of a black hole. Time slows down. The basic idea is that gravity doesn't just pull on matter. It doesn't just pull on energy. Gravity, in a sense, pulls on time itself, or even more precisely, gravity is the warping of time. Gravity is manifested by the fact that clocks at different distances from a gravitational source will tick off time at different rates. First of all, talking about the entire universe inside a black hole is a bit extreme, but what I would say is, it is possible that, at least according to the traditional general relativistic description of black holes, I'm not going to modify it with modern or more recent conjectures, speculations about firewalls and all that sort of good stuff. So let's just act as though Einstein had the important word on black holes, which may not be the case. But if that's true, then right now it's quite conceivable that the Earth just passed across the edge of a black hole, that we are all now inside of a black hole. Why is that? The edge of a black hole, in Einstein's description, is not some special location in space. It's just an ordinary chunk of space that has the unusual property that once you pass that location, the event horizon, you're no longer able to get out. But you don't have any direct physical reaction to crossing over the event horizon of a black hole. So right now, everything, as we look around the world, we could all be within a black hole, and we'll only really recognize that later on when we get closer and closer to the center of the black hole, because then, depending on our precise distance from the black hole, different parts of the Earth, different parts of our body will feel a different force. If we are going feet first toward the center of a black hole, our feet will experience a greater pull than our head. Our body will be stretched. Spaghettified is the technical term that we use for this process, until ultimately we're pulled apart into our constituent particles that will all rain down on the singularity, whatever that is, the center of the black hole. We don't really understand what goes on there. So in that sense, we could all be within a black hole right now. We currently witness that the expansion of the universe is speeding up, not slowing down. The observations in 1998, culminated in 1998, which won the 2011 Nobel Prize, showed that the distant galaxies are moving away ever more quickly. The expansion of space is speeding up over time. It's accelerating. How do we explain that? The best explanation we currently have is repulsive gravity. We believe even today the universe is suffused with a bath of energy. We call it dark energy. We believe it's uniformly going through space. I like to think of it almost like as a Turkish sauna. It's like the steam filling the sauna, this energy filling space. And that repulsive gravity, we believe, is responsible for the observations that the distant galaxies are rushing away faster and faster over time. So it's circumstantial, but the case for repulsive gravity is quite strong.